Hey guys, tonight we are diving into one of the ocean's most quietly spectacular mysteries, floating 3 miles beneath the surface where you would definitely not survive the crushing pressure, watching translucent jellyfish drift through absolute darkness like living ghosts, following invisible roads you cannot see. You are suspended in this alien world, witnessing creatures that have mastered navigation without GPS, without landmarks, without even a brain to process complex directions, yet somehow they know exactly where they are going across thousands of miles of empty blue space. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Drop a comment letting me know where you are watching from tonight and what time it is in your part of the world. I always love seeing how this community spans across time zones and continents. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You float here in the deep Pacific, watching a moon jellyfish pulse gently through the water column, its bell contracting and expanding in that hypnotic rhythm that has remained unchanged for over 500 million years. But what you are witnessing tonight is not just ancient elegance, it is navigation technology that would make modern engineers weep with envy. This jellyfish, no bigger than a dinner plate and possessing roughly the same intellectual capacity as your average houseplant, is following an invisible superhighway that stretches across entire ocean basins. The discovery happened almost by accident, as the best discoveries often do. You are watching marine biologist Dr. Sarah Chen in 2019 tracking tagged jellyfish off the coast of California using satellite technology originally designed for studying whale migration. She expected random drifting, creatures at the mercy of currents and tides, but instead her data revealed something extraordinary. The jellyfish were not wandering aimlessly, they were commuting, perfect straight lines across hundreds of miles, synchronized movements that suggested they were following some kind of invisible infrastructure beneath the waves. You observe Chen's team as they overlay the jellyfish tracking data with magnetic field maps of the ocean floor, and suddenly the pattern becomes crystal clear. The jellyfish routes align perfectly with Earth's magnetic field lines, those invisible forces that guide compass needles and migrating birds, now revealed to be operating 3 dimensions deeper than anyone had imagined. These translucent drifters, creatures without eyes that could see magnetic fields or brains that could process complex navigation, were somehow reading the planet's magnetic signature like a subway map. Researchers still argue about how long this phenomenon has been occurring, with some suggesting that jellyfish magnetic navigation predates the evolution of vertebrates entirely. You watch as paleontologists examine fossilized jellyfish impressions from the Cambrian period, finding mineral deposits that suggest magnetic sensitivity stretching back over 500 million years, making these creatures among Earth's first magnetic navigators, pioneers of a technology that would eventually evolve in everything from sea turtles to migratory birds. The implications ripple outward like waves from a dropped stone. You are witnessing creatures that essentially treat the Earth like one massive navigation system, following magnetic highways that remain stable across geological timescales, routes that were established when continents were in completely different positions, when the ocean looked nothing like the blue marble you know today. You drift closer to examine the moon jellyfish from the previous observation, its translucent bell pulsing steadily as you peer into its simple anatomy, searching for the secret of magnetic detection. The creature before you appears almost impossibly primitive, 95% water with no brain, no blood, no central nervous system, yet somehow it processes magnetic information with precision that rivals sophisticated electronic instruments. You are looking at a living compass that operates on principles scientists are still struggling to understand. Inside the jellyfish's bell, scattered throughout tissue so transparent you can see right through it, you discover microscopic crystals of magnetite, the same iron oxide mineral that forms natural magnets. These crystals, each smaller than a grain of pollen, are arranged in chains like tiny beads on invisible strings, creating biological magnetometers that respond to Earth's magnetic field with exquisite sensitivity. You watch as these crystals orient themselves along magnetic field lines, sending signals through the jellyfish's simple neural network, a process so elegant it makes human engineering look clunky by comparison. The magnetite crystals function like a three-dimensional compass, providing information not just about direction, but also about magnetic field intensity and inclination. You observe how the jellyfish can detect variations in magnetic field strength that would require sensitive laboratory equipment for humans to measure. This gives them a magnetic map of the ocean floor, with underwater mountain ranges, deep trenches, and metal deposits, all creating distinctive magnetic signatures that serve as landmarks on their invisible highways. Dr. Chen's team discovered that different species of jellyfish possess varying concentrations of these magnetite crystals, which correlates directly with their navigation abilities. You examine a massive lion's mane jellyfish, its bell spanning 6 feet across, packed with magnetite crystals that allow it to navigate with stunning accuracy across vast distances. Compare this to smaller coastal species with fewer crystals, creatures that stick to local waters and seem content to drift with regional currents rather than attempt long-distance magnetic travel. The sensitivity of this magnetic detection system becomes apparent when you observe jellyfish responding to magnetic anomalies that are completely invisible to human senses. You watch a group of jellyfish approaching an underwater volcanic vent, where iron-rich minerals create local magnetic distortions. The creatures slow their movement, testing the magnetic environment like cautious drivers navigating construction zones, adjusting their routes to avoid areas where magnetic signals become unclear or contradictory. Researchers still argue about whether jellyfish consciously navigate or simply follow magnetic gradients instinctively, but the evidence suggests something far more sophisticated than random drift. You witness jellyfish making deliberate course corrections when they encounter magnetic obstacles, behaviors that suggest active decision-making despite their simple nervous systems. These creatures appear to possess an innate understanding of magnetic geography that humans can only approximate with complex instruments and detailed charts. The evolutionary advantages of magnetic navigation become obvious when you consider the jellyfish's lifestyle. These are creatures that must find specific water temperatures, particular nutrient concentrations, and appropriate breeding grounds across vast oceanic distances. Random drifting would be evolutionary suicide, but magnetic navigation allows them to efficiently locate optimal habitats with minimal energy expenditure, following established routes that have been tested and refined over millions of years. You observe the magnetite crystals responding to changes in Earth's magnetic field in real time, tiny compass needles constantly adjusting as the jellyfish moves through different magnetic zones. This creates a continuous stream of navigational information, like having a GPS system that never needs satellite updates because it reads the planet's magnetic infrastructure directly. The jellyfish processes this information through neural pathways so simple they barely qualify as a nervous system, yet somehow achieve navigation accuracy that modern technology struggles to match. The magnetic detection system also appears to provide information about depth and vertical position in the water column, as Earth's magnetic field varies with altitude above the ocean floor. You watch jellyfish adjusting their buoyancy in response to magnetic cues, maintaining optimal positions within their preferred depth ranges, even in areas where visual or chemical landmarks are completely absent. You are transported back through geological time, floating above ancient sea floors where the first magnetic highways were being established, watching the slow dance of tectonic plates and shifting magnetic fields that created the navigation routes jellyfish follow today. The ocean beneath you bears no resemblance to the modern Pacific, continents scattered in unfamiliar configurations, yet already primitive jellyfish ancestors were learning to read the planet's magnetic signature, establishing migration patterns that would persist across deep time. The magnetic field lines you observed in the previous section have remained remarkably stable for millions of years, creating permanent superhighways that span entire ocean basins. You trace these invisible routes as they stretch from the Arctic Ocean down through the Pacific, following magnetic anomalies created by underwater mountain ranges, ancient meteor impact sites, and massive iron ore deposits embedded in the seafloor. These geological features act like magnetic lighthouses, providing consistent navigational references that jellyfish have relied upon since before the first fish evolved. Dr. Martinez, a marine geologist studying magnetic navigation, shows you sonar maps revealing how jellyfish migration routes align perfectly with mid-ocean ridges, those underwater mountain chains where new seafloor is continuously created. You watch modern jellyfish following paths that were established when their ancestors navigated around volcanic islands that have long since eroded away, routes preserved in the magnetic memory of the ocean floor like fossilized highways. The stability of these magnetic routes becomes particularly fascinating when you consider the dramatic changes Earth has experienced over geological time. You witness ice ages that locked vast quantities of water in continental glaciers, lowering sea levels by hundreds of feet, yet jellyfish continued following the same magnetic pathways, adjusting only for depth changes, while maintaining their fundamental directional preferences. These creatures were commuting along established routes when dinosaurs ruled the land, and they are still using the same highways today. The discovery of magnetic route persistence emerged from studying jellyfish fossils, those rare impressions preserved in sedimentary rock that reveal ancient migration patterns. You examine fossil beds in Montana, once an ancient seabed, where jellyfish impressions are aligned in consistent directional patterns that match modern magnetic field orientations. The routes these creatures follow today were already ancient when the first mammals appeared, navigation to superhighways older than entire mountain ranges. Researchers still argue about how much of this navigation behavior is genetically programmed versus learned through environmental cues, but the evidence suggests a combination of both factors. You observe juvenile jellyfish instinctively orient along magnetic field lines, displaying navigation preferences they could not have learned through experience. Yet you also notice subtle variations in route selection that suggest some degree of adaptation to changing conditions, a flexibility that allows ancient navigation systems to accommodate modern environmental changes. The interconnected nature of these magnetic highways becomes apparent when you map global jellyfish migration patterns, revealing a network that spans all major ocean basins like an underwater interstate system. You follow routes that connect Arctic feeding grounds to tropical breeding areas, pathways that allow genetic exchange between jellyfish populations separated by thousands of miles. This magnetic infrastructure supports global jellyfish ecology on a scale that rivals any terrestrial migration system. Climate change adds new complexity to these ancient patterns as shifting ocean temperatures and changing currents interact with stable magnetic highways in unpredictable ways. You witness jellyfish following traditional magnetic routes into waters that no longer provide suitable habitat, creating evolutionary pressure that may force these ancient navigation systems to adapt or fail. The magnetic highways remain constant, but the destinations they lead to are changing faster than jellyfish evolution can accommodate. The precision of these long-distance migrations rivals anything achieved by more complex animals. Yet jellyfish accomplish this feat with neural systems so simple they consist of loose networks of interconnected cells rather than centralized brains. You are watching creatures that navigate with the accuracy of GPS systems while possessing roughly the same computational power as a basic calculator, following routes that connect feeding areas in Alaska to breeding grounds near Hawaii, with timing synchronized to seasonal changes across vast distances. You find yourself inside a sterile laboratory in Woods Hole, watching Dr. Yamamoto carefully lower a moon jellyfish into a specially designed tank surrounded by electromagnetic coils, the kind of equipment that would make a physics professor jealous. This is where the theoretical becomes tangible, where those magnetite crystals you observed earlier prove their remarkable abilities under controlled conditions that strip away every variable except pure magnetic response. The experimental setup resembles something from a science fiction movie. Circular tanks surrounded by precisely calibrated magnetic field generators that can replicate Earth's magnetic environment or create entirely artificial magnetic landscapes. You watch as the jellyfish settles into the center of the tank, its bell pulsing in that familiar rhythm, completely unaware that it has become the subject of one of marine biology's most elegant experiments. Dr. Yamamoto activates the magnetic field generators, creating an artificial magnetic north that points directly opposite to Earth's actual magnetic field, and the response is immediate and unmistakable. The jellyfish, which had been drifting randomly in the neutral magnetic environment, suddenly orients itself toward the artificial magnetic source and begins swimming in that direction with purpose that would impress a homing pigeon. You are witnessing magnetic navigation in its purest form, stripped of ocean currents, temperature gradients, and every other environmental factor that might influence movement. The precision of the magnetic response becomes even more remarkable when you observe the jellyfish reacting to subtle changes in field intensity that register on sensitive magnetometers but would be completely imperceptible to human senses. Dr. Yamamoto gradually weakens the artificial magnetic field, and you watch the jellyfish slow its directed movement, testing the magnetic environment like a person squinting to read fine print, until the field strength drops below detection threshold and the creature returns to random drifting. The most stunning demonstration occurs when multiple magnetic field generators create complex magnetic landscapes within the tank, simulating the kind of magnetic terrain jellyfish encounter in the open ocean. You observe the jellyfish navigating between artificial magnetic mountains and valleys, following magnetic contours with the skill of an experienced pilot reading topographical maps. The creature chooses optimal routes through magnetic obstacles, displaying navigation intelligence that seems impossible given its simple neural architecture. Different species respond to magnetic fields with varying degrees of sensitivity and sophistication, revealing an evolutionary spectrum of magnetic navigation abilities. You watch box jellyfish, those venomous tropical species, demonstrate magnetic detection capabilities that surpass even the impressive moon jellies from earlier observations. Their magnetic responses are faster, more precise, and capable of detecting field variations that barely register on laboratory instruments, suggesting that magnetic navigation has been refined through evolutionary pressure into something approaching perfection. Researchers still argue about the exact mechanism by which magnetite crystals translate magnetic field information into neural signals, but the behavioral evidence is undeniable. You witness jellyfish performing magnetic navigation tasks that would require complex calculations if attempted by artificial intelligence. Yet these creatures accomplish the same feats using biological processes that operate below the threshold of conscious thought. The laboratory experiments also reveal how jellyfish integrate magnetic information with other sensory inputs, creating navigation systems more sophisticated than their simple anatomy suggests possible. You observe jellyfish responding to combinations of magnetic fields and water temperature changes, demonstrating that magnetic navigation works in concert with thermal detection to create three-dimensional maps of ocean conditions. This multisensory approach allows jellyfish to find not just magnetic routes, but optimal routes that provide favorable temperatures and chemical conditions along the way. The controlled environment allows researchers to test jellyfish responses to magnetic conditions that would be impossible to recreate in nature, including magnetic field reversals that simulate what happens during Earth's periodic magnetic pole switches. You watch jellyfish adapting to reversed magnetic fields within hours, reorienting their navigation preferences with flexibility that suggests magnetic navigation systems evolved to accommodate the planet's magnetic instability over geological time. The implications extend far beyond jellyfish biology, as understanding magnetic navigation mechanisms could inspire new approaches to autonomous underwater vehicle design and bio-inspired navigation technologies that operate without satellite signals or external references. You descend toward the mid-Atlantic ridge, that massive underwater mountain range where molten rock continuously emerges from Earth's interior, creating magnetic chaos that turns the ocean floor into a navigational maze. The familiar magnetite crystals you observed in a laboratory jellyfish earlier encounter their greatest challenge here, where competing magnetic signatures from iron-rich volcanic rocks create the equivalent of magnetic traffic jams that can confuse even the most sophisticated biological navigation systems. The ridge system stretches like a giant scar across the ocean floor, its volcanic peaks rising thousands of feet from the abyssal plains, each eruption depositing layers of magnetized basalt that record Earth's magnetic field orientation at the moment of cooling. You observe how these magnetic stripes create a complex pattern of alternating magnetic polarities, like a geological barcode that reveals the planet's magnetic history stretching back millions of years, but also creates navigation obstacles that jellyfish must somehow overcome. Dr. Hassan's research vessel follows a group of crystal jellyfish as they approach a particularly active section of the ridge system, where recent volcanic activity has created fresh magnetic anomalies. You watch the jellyfish slow their forward progress, their bells contracting more frequently as they encounter conflicting magnetic signals that would scramble any conventional compass. The creatures begin displaying behavior patterns you have not seen before, circular swimming motions that suggest they are actively testing different magnetic orientations to find a path through the magnetic confusion. The magnetic dead zones created by underwater metal deposits present even greater navigation challenges, areas where competing magnetic fields cancel each other out, leaving biological magnetometers with no clear directional guidance. You observe jellyfish entering these magnetic null zones and immediately beginning what researchers call search behavior, expanding spiral swimming patterns that gradually widen until they detect the edge of clearer magnetic signals, like blind people feeling for walls in an unfamiliar room. Some jellyfish species have evolved remarkable solutions to magnetic navigation challenges, developing what appears to be magnetic memory that allows them to maintain course direction even when passing through areas of magnetic interference. You watch Pacific sea nettles maintaining consistent southward movement while crossing a magnetic anomaly zone that would completely disorient creatures relying solely on real-time magnetic detection, suggesting these animals can remember magnetic bearings and continue following them during periods of signal confusion. Researchers still argue about whether jellyfish can distinguish between natural magnetic anomalies and artificial magnetic interference from human activities, but shipping lanes present obvious navigation challenges. You observe jellyfish near major shipping routes, encountering magnetic disturbances from passing cargo vessels. Those massive steel hulls that create traveling magnetic anomalies, strong enough to deflect compass needles on surface vessels. Yet somehow the jellyfish adapt their routes to accommodate this magnetic pollution. The most fascinating magnetic navigation challenges occur at the boundaries between ocean basins, where different magnetic provinces meet and create transitional zones of complex magnetic topology. You follow a group of moon jellies you first encountered in Section 1 as they approach the boundary between Pacific and Atlantic magnetic domains, navigating through areas where magnetic field orientations change gradually over hundreds of miles, requiring continuous recalibration of their biological compass systems. Deep ocean trenches create their own unique magnetic environments, as the extreme depth places these areas closer to Earth's magnetic field generation in the planet's core, while sediment layers accumulated over millions of years create magnetic shielding effects that filter certain magnetic signals. You observe jellyfish adjusting their swimming depth as they traverse the Puerto Rico Trench, diving deeper when magnetic signals become unclear at shallower depths, demonstrating three-dimensional magnetic navigation that operates across the entire water column. The interaction between magnetic navigation and ocean currents becomes particularly complex in areas where strong currents flow across magnetic field lines, creating the equivalent of magnetic crosswinds that jellyfish must compensate for while maintaining their intended courses. You watch jellyfish swimming at angles to their intended direction, like aircraft compensating for wind drift, maintaining magnetic bearings while allowing current flow to carry them toward their ultimate destinations. Volcanic islands create particularly interesting magnetic navigation challenges, as their basaltic composition generates local magnetic fields strong enough to overwhelm Earth's background magnetic signature within several miles of shore, creating magnetic interference zones where normal navigation becomes impossible, and jellyfish must rely on alternative navigation cues to avoid becoming permanently disoriented. You surface near the coast of Japan, where an unprecedented phenomenon is unfolding. Millions upon millions of jellyfish crowding coastal waters in concentrations that transform the sea into a living, pulsing carpet of translucent bells. This is what happens when magnetic navigation systems encounter disruption on a massive scale, creating traffic jams in those invisible highways you have been following, forcing creatures that normally spread across vast oceanic distances into confined spaces where they compete for resources and struggle to continue their ancient migration patterns. The jellyfish bloom stretches as far as you can see. Moon jellies, crystal jellies, and sea nettles mix together in densities that reach thousands of individuals per cubic meter, their combined movement creating currents and pressure waves that interfere with the magnetic navigation of surrounding marine life. You observe fishing boats struggling to deploy nets through the gelatinous mass, their engines clogged with jellyfish tissue, while local ecosystems buckle under the pressure of this unexpected biological invasion. Dr. Chen, whom you first encountered tracking jellyfish migration patterns, has followed these blooms to their source, discovering that many of the largest jellyfish aggregations occur at points where magnetic field anomalies intersect with ocean current boundaries, creating natural collection points where normal navigation breaks down. You watch her team deploying magnetometers alongside the massive bloom, revealing magnetic field disturbances that correlate directly with jellyfish density patterns, suggesting these creatures become trapped by the same magnetic features that normally guide their movements. The formation of jellyfish superhighways that you traced through ancient geological formations now works against the animals, as increased shipping traffic, underwater construction, and electromagnetic pollution from submarine cables create artificial magnetic landmarks that disrupt established migration routes. You observe jellyfish following magnetic signals generated by a new undersea fiber optic cable, swimming in precise formation along a completely artificial magnetic pathway that leads them away from traditional feeding grounds toward nutrient-poor waters where they cannot sustain themselves. Climate change amplifies the magnetic traffic jam phenomenon, as warming ocean temperatures force jellyfish to seek cooler waters along migration routes that may not align with their magnetic navigation preferences. You witness massive blooms forming where cold upwelling currents intersect with magnetic highways, creating bottlenecks where jellyfish following ancient magnetic routes encounter environmental conditions that slow their movement and cause progressive accumulation of individuals over multiple migration cycles. The ecological consequences ripple outward like waves from the jellyfish blooms themselves, as these massive aggregations consume zooplankton and small fish at rates that deplete local food webs faster than natural processes can replenish them. You observe seabirds diving repeatedly into the jellyfish swarms, their beaks and throats clogged with gelatinous tissue that provides minimal nutrition while preventing them from catching more suitable prey, creating secondary effects that propagate through multiple levels of marine ecosystems. Researchers still argue about whether jellyfish blooms represent temporary disruptions that will resolve as magnetic navigation systems adapt, or permanent changes that indicate fundamental breakdown of ancient migration patterns. You watch satellite imagery revealing bloom formation patterns that suggest some jellyfish populations are abandoning traditional magnetic routes entirely, developing new navigation strategies that rely more heavily on chemical gradients and temperature differences than magnetic field detection. Power plant cooling systems become inadvertent jellyfish collectors, as warm water discharge creates thermal signatures that interfere with temperature-sensitive navigation systems, while the electromagnetic fields generated by high-voltage power transmission create magnetic beacons that attract jellyfish from unexpected directions. You observe nuclear power facilities on coastal areas, dealing with intake systems clogged by jellyfish, following artificial magnetic and thermal signals that lead them directly into industrial infrastructure. The social structure of jellyfish blooms reveals unexpected complexity, as individual navigation decisions influenced by magnetic field disruptions create collective movement patterns that can persist for weeks or months. You notice how jellyfish within large aggregations begin synchronizing their swimming rhythms, creating coordinated movement that suggests communication between individuals, despite their simple nervous systems, possibly through pressure waves or chemical signals that compensate for magnetic navigation failures. The phenomenon extends beyond local coastal impacts, as major jellyfish blooms can alter regional ocean chemistry and nutrient distribution patterns, creating cascade effects that influence the magnetic navigation abilities of other marine species. By changing the chemical and thermal landmarks these animals use to complement their magnetic senses. You are floating in space now, watching solar storms erupting from the sun's surface, massive ejections of charged particles streaming toward Earth at speeds that make terrestrial hurricanes look like gentle breezes. These celestial events, invisible to human senses but devastating to magnetic navigation systems, create electromagnetic chaos that reaches deep into the ocean, disrupting the same magnetic highways you have been following, turning reliable navigation routes into confusing mazes that leave jellyfish wandering lost in the vast blue void. The solar storm strikes Earth's magnetosphere like a hammer blow, compressing magnetic field lines and creating fluctuations that register on magnetometers worldwide, but the effects penetrate much deeper than most people realize. You descend back into the ocean to observe how these space weather events interfere with the magnetite crystals in jellyfish tissue, those microscopic compass needles becoming unreliable as Earth's magnetic field fluctuates wildly under bombardment from solar radiation. Dr. Patel's research station in the Azores has been monitoring jellyfish behavior during geomagnetic storms, correlating space weather data with marine biology observations to understand how extraterrestrial events influence ocean ecosystems. You watch her team tracking tagged jellyfish during a particularly severe solar storm, observing how creatures that normally maintain precise headings begin swimming in confused circles, their magnetic navigation systems overwhelmed by signals that change faster than biological processes can accommodate. The disruption extends beyond simple directional confusion, as solar storms can temporarily reverse local magnetic field orientations, causing jellyfish to swim in exactly the wrong direction while following magnetic signals they interpret as correct. You observe moon jellies that should be heading south toward warm water breeding grounds, instead swimming north toward Arctic waters where temperatures would quickly kill them, following magnetic signatures corrupted by solar radiation that makes magnetic north appear to be magnetic south. Communication between jellyfish appears to break down during severe geomagnetic disturbances, as the pressure waves and chemical signals that complement magnetic navigation become unreliable when magnetic reference points shift unpredictably. You witness large groups of jellyfish that normally move in coordinated formations, fragmenting into individual wanderers, each following slightly different interpretations of corrupted magnetic signals that lead them in divergent directions across the ocean surface. The intensity and duration of solar storms determine their impact on marine navigation systems, with minor geomagnetic disturbances causing temporary course corrections that jellyfish can accommodate through their search behavior patterns, while major solar events can completely scramble magnetic navigation for days or weeks. You observe the aftermath of a severe solar storm, finding jellyfish scattered across ocean areas where they would never normally be present, creatures that followed disrupted magnetic signals into ecological dead zones, far from suitable habitat. Researchers still argue about whether jellyfish can sense approaching geomagnetic storms before they reach maximum intensity, possibly through detection of subtle magnetic field changes that precede major space weather events, but behavioral evidence suggests some species alter their migration timing to avoid the worst effects of solar radiation. You notice jellyfish beginning evasive movements hours before magnetometer readings indicate significant geomagnetic disturbance, possibly responding to magnetic field fluctuations too subtle for human instruments to detect reliably. The evolutionary implications of solar storm interference become apparent when you consider that geomagnetic disturbances have been affecting Earth throughout the planet's history, creating selective pressure that favored jellyfish with robust magnetic navigation systems capable of maintaining course during periods of magnetic field instability. Those magnetite crystals you examined earlier may represent millions of years of evolution, fine-tuning biological compass systems to function reliably despite interference from space weather. Recovery patterns following major solar storms reveal the resilience of magnetic navigation systems as jellyfish gradually reorient themselves along correct magnetic bearings once Earth's magnetic field stabilizes, though the process can take weeks for widely scattered populations to reorganize into normal migration patterns. You watch jellyfish using their search behavior techniques to relocate disrupted magnetic highways, swimming in expanding spirals until they detect familiar magnetic signatures that guide them back toward traditional migration routes. Modern technology adds new complexity to solar storm impacts, as electromagnetic pulse effects from severe space weather can damage or destroy electronic navigation equipment on research vessels, making it difficult for scientists to study jellyfish magnetic navigation precisely when these systems face their greatest challenges from natural magnetic field disruptions. You are soaring across the Pacific Ocean at satellite altitude, tracing the longest magnetic superhighway on Earth, a vast invisible corridor that stretches over 6,000 miles from the volcanic islands of Japan to the California coast. This is the Great Pacific Jellyfish Superhighway, a magnetic navigation route so massive and well established that millions of jellyfish use it simultaneously, creating what amounts to the ocean's busiest commuter route, complete with traffic patterns, seasonal rush hours, and navigational challenges that would impress any urban transportation planner. The superhighway follows the Kuroshio Current system, where warm tropical waters carry nutrients northward along the coast of Japan before turning eastward across the Pacific. But the jellyfish are not simply drifting with the current flow. You observe them maintaining precise magnetic bearings that cut across current directions, sometimes swimming at sharp angles to water movement to stay within magnetic field corridors that provide optimal navigation conditions, demonstrating that magnetic guidance overrides passive drift in determining their migration routes. Dr. Nakamura's research team has spent 5 years mapping this trans-Pacific migration route, deploying satellite-tracked buoys equipped with magnetometers and underwater cameras that document the incredible density and diversity of jellyfish traffic along the magnetic superhighway. You watch their footage revealing processions of different species traveling in distinct layers within the water column, moon jellies near the surface, crystal jellies at intermediate depths, and massive lion's mane jellyfish cruising along the bottom of the magnetic corridor like biological cargo ships. The seasonal timing of superhighway traffic follows patterns that connect feeding opportunities in Alaskan waters with breeding grounds in the subtropical Pacific, creating migration cycles that span multiple years and cover distances that challenge even the most accomplished oceanic travelers. You observe jellyfish beginning their eastbound journey in Japanese coastal waters during spring, following magnetic field lines that guide them through optimal temperature zones as ocean conditions change with seasonal progression. Navigation challenges along the superhighway include the Emperor Seamount Chain, those underwater mountains that create magnetic anomalies strong enough to disrupt normal compass function, forcing jellyfish to develop alternative navigation strategies for crossing these magnetic obstacle courses. You watch experienced migrators following specific routes around known magnetic disturbances, paths that have been refined through countless generations of trial and error into optimized corridors that minimize navigation confusion while maintaining efficient progress toward distant destinations. The convergence of multiple species along the same magnetic highway creates complex ecological interactions as different jellyfish types compete for the same optimal magnetic navigation zones while maintaining species-specific depth preferences and feeding behaviors. You observe lion's mane jellyfish claiming the deepest portions of the magnetic corridor, their massive size allowing them to dominate prime navigation space, while smaller species concentrate in shallower waters where magnetic signals may be less precise but competition is reduced. Mid-ocean navigation requires jellyfish to maintain course accuracy across thousands of miles of open water where visual landmarks are completely absent and ocean conditions provide few reliable reference points besides magnetic field orientation. You witness the remarkable precision with which jellyfish maintain headings across the central Pacific, following magnetic bearings with accuracy that rivals GPS navigation despite using biological systems that evolved millions of years before electronic technology. Researchers still argue about how jellyfish navigate around the massive garbage patches that have accumulated along Pacific current systems, as these floating debris fields create both physical obstacles and electromagnetic interference from metallic waste that disrupts local magnetic field patterns. You observe jellyfish adjusting their routes to avoid areas of heavy plastic pollution, possibly responding to chemical signals or magnetic anomalies created by concentrated debris. The superhighway terminates in California coastal waters, where upwelling currents provide rich feeding opportunities that support jellyfish populations through winter months before the return migration begins, following slightly different magnetic routes that account for seasonal changes in ocean temperature and current patterns. You watch jellyfish gathering in massive aggregations off the California coast, their journey across the world's largest ocean completed with timing precision that allows them to exploit optimal feeding conditions. Climate change impacts on the superhighway include shifting ocean temperatures that affect the thermal layering jellyfish use to complement magnetic navigation, potentially forcing these ancient migration routes to adapt to environmental conditions that change faster than evolutionary processes can accommodate, creating uncertainty about the long-term viability of trans-Pacific jellyfish migration patterns. You are traveling backward through evolutionary time, watching the gradual development of magnetic sensitivity in jellyfish ancestors across hundreds of millions of years, observing how environmental pressures shaped the magnetite crystal systems you have been following throughout this journey. The story begins in Precambrian oceans, where primitive jellyfish relatives first encountered magnetic minerals in their environment, accidentally incorporating iron particles that would eventually evolve into the sophisticated biological compass systems that guide modern jellyfish across vast oceanic distances. The earliest magnetic detection capabilities likely emerged from simple ion storage mechanisms, as primitive marine organisms required iron for basic cellular functions and began concentrating iron-rich particles in specialized tissue structures that coincidentally responded to Earth's magnetic field orientation. You observe ancient jellyfish relatives developing rudimentary directional preferences based on magnetic field alignment, behaviors that provided survival advantages in environments where random movement could lead to starvation or exposure to dangerous conditions. Dr. Evolution's research team, studying fossilized jellyfish impressions from around the world, has discovered evidence suggesting that magnetic navigation evolved independently in multiple jellyfish lineages, indicating that environmental pressures consistently favored creatures capable of detecting and responding to magnetic field variations. You examine fossil specimens from Australia, China, and North America, each showing mineral deposits consistent with magnetite crystal development, suggesting that magnetic sensitivity became a fundamental survival requirement for free-swimming marine organisms. The refinement of magnetic navigation capabilities accelerated during periods of dramatic environmental change as ice ages, volcanic activity, and continental drift created rapidly changing oceanic conditions that favored organisms capable of navigating efficiently across large distances to find suitable habitat. You witness evolutionary pressure selecting for increasingly sophisticated magnetite crystal arrangements, from simple ion clusters to the precisely organized chains of magnetic particles that characterize modern jellyfish navigation systems. Different jellyfish species display varying levels of magnetic sensitivity that reflect their evolutionary histories and ecological requirements, with highly migratory species possessing more refined magnetite crystal systems than coastal species that rely primarily on local environmental cues for navigation. You observe box jellyfish, those efficient predators from warm tropical waters, demonstrating magnetic detection capabilities that surpass most other jellyfish species, suggesting that active hunting lifestyles drove evolution of enhanced navigational precision. The development of magnetic memory capabilities represents a particularly sophisticated evolutionary advancement, allowing jellyfish to maintain course direction during periods when magnetic signals become unreliable due to geological or solar interference. You watch Pacific sea nettles demonstrating this ability, maintaining consistent migration headings while crossing magnetic anomaly zones that would completely disorient species lacking magnetic memory systems, an evolutionary adaptation that required millions of years to develop. Researchers still argue about the relationship between jellyfish brain evolution and magnetic navigation capabilities, as these creatures developed increasingly sophisticated magnetic detection systems while maintaining extremely simple nervous system organization that challenges traditional assumptions about the neural requirements for complex navigation behaviors. The magnetite crystals you examined earlier appear to process navigational information through mechanisms that operate below the threshold of conscious thought, suggesting evolutionary solutions that bypass the need for complex central nervous systems. Geographic isolation created different evolutionary pressures that shaped distinct magnetic navigation strategies in jellyfish populations separated by oceanic barriers, leading to species-specific approaches to magnetic field interpretation that reflect millions of years of adaptation to local magnetic environments. You observe Arctic jellyfish species that evolved enhanced magnetic sensitivity to navigate in polar regions where magnetic field inclination creates unique navigational challenges compared to tropical environments. The co-evolution of magnetic navigation with other sensory systems created integrated navigation approaches that combine magnetic detection with thermal sensing, chemical gradient detection, and pressure sensitivity to create multidimensional maps of ocean conditions. You witness modern jellyfish using combinations of magnetic bearings and temperature gradients to locate optimal feeding areas, navigation strategies that evolved through trial and error across countless generations of oceanic travelers. Climate change presents new evolutionary pressures that may drive further adaptation of magnetic navigation systems as changing ocean temperatures and shifting current patterns interact with stable magnetic highways in ways that challenge traditional navigation strategies, potentially favoring jellyfish populations capable of developing more flexible approaches to magnetic field interpretation that can accommodate rapidly changing environmental conditions. You find yourself in a research facility of the near future, where Dr. Chen's granddaughter is studying predictive models that combine jellyfish magnetic navigation data with climate change projections, creating maps that forecast how ancient oceanic highways will function in a rapidly transforming world. The same magnetic routes you have followed throughout this journey remain constant, but their destinations are shifting as warming waters and changing currents create entirely new oceanic landscapes that jellyfish navigation systems must somehow accommodate. The magnetic superhighways that have guided jellyfish for millions of years now lead to unfamiliar territories as Arctic ice melts, create new water masses with different magnetic signatures, while equatorial regions become too warm for traditional jellyfish populations, forcing these ancient travelers to explore magnetic pathways that lead to previously unsuitable habitats. You observe computer simulations showing jellyfish following established magnetic routes into areas where their descendants may need to evolve completely different survival strategies. Marine protected areas designed around magnetic navigation patterns represent a revolutionary approach to ocean conservation, as scientists recognize that preserving jellyfish migration routes requires protecting not just feeding and breeding areas, but the invisible magnetic corridors that connect them across entire ocean basins. You watch planners creating conservation boundaries that follow magnetic field lines rather than political borders, establishing protected zones that accommodate the three-dimensional reality of magnetic navigation through the water column. The integration of jellyfish magnetic navigation research with autonomous underwater vehicle development has created bio-inspired navigation systems that operate without GPS signals or external references, using artificial magnetite sensors modeled on jellyfish magnetic detection capabilities. You observe prototype underwater drones following the same magnetic highways that guide jellyfish, demonstrating navigation accuracy that rivals biological systems, while providing new tools for monitoring ocean conditions along established marine migration routes. Aquaculture applications of magnetic navigation research include facilities designed to work with natural jellyfish behavior rather than against it, creating jellyfish farms positioned along magnetic highways, where wild populations naturally concentrate, reducing the energy costs and environmental impacts associated with artificial jellyfish cultivation. You witness experimental facilities that use magnetic field generators to guide jellyfish movement within contained areas, essentially creating artificial magnetic environments that mimic natural navigation conditions. Researchers still argue about the long-term viability of magnetic navigation in an increasingly electromagnetic world, as submarine cables, offshore wind farms, and shipping traffic create artificial magnetic signatures that may eventually overwhelm natural magnetic field patterns, but adaptive responses observed in modern jellyfish populations suggest these navigation systems possess evolutionary flexibility that may accommodate technological interference through behavioral adjustments rather than genetic changes. The discovery of magnetic navigation capabilities in other marine organisms, from sea turtles to certain fish species, reveals that jellyfish were pioneers of navigation technology that has been independently adopted throughout marine ecosystems, suggesting that magnetic field detection represents a fundamental solution to oceanic navigation challenges that transcends individual species boundaries. You observe research teams studying magnetic navigation across entire marine food webs, understanding how electromagnetic interference affects ecosystem-wide navigation patterns. Educational applications of jellyfish magnetic navigation research include school programs that use these creatures as examples of biological engineering excellence, inspiring new generations of scientists and engineers to develop sustainable navigation technologies based on principles that have been tested and refined through millions of years of evolutionary optimization. You watch students building magnetic navigation experiments using jellyfish-inspired designs, learning scientific principles through hands-on exploration of biological magnetic detection systems. The philosophical implications extend beyond practical applications, as understanding how jellyfish navigate using Earth's magnetic field reveals the deep interconnection between life and planetary systems, demonstrating that organisms are not separate from their environment, but intimately connected to geological and astronomical processes that operate on scales far beyond individual lifespans. The magnetite crystals you have observed throughout this journey represent a direct physical link between living creatures and the planet's magnetic field, making jellyfish living components of Earth's magnetic system rather than simply organisms that happen to detect magnetic fields. You float here at the end of this journey, understanding that magnetic navigation represents just one example of the countless invisible connections that link life to planetary processes, reminding us that the ocean contains layers of complexity and beauty that remain largely hidden from casual observation, yet operate continuously beneath the waves. The jellyfish drift quietly now in the deepening twilight of your imagination, their translucent bells pulsing gently as they follow magnetic pathways that stretch across dark waters like silver threads connecting distant shores. You have witnessed their ancient wisdom, watched them navigate by reading the planet's invisible signature with precision that makes human technology seem clumsy by comparison. Yet they accomplish this feat with such elegant simplicity that it appears effortless, almost dreamlike in its graceful efficiency. The magnetite crystals within their tissue continue their silent work, tiny compass needles pointing toward destinations that exist beyond the horizon of human understanding, following roads established when the world was young and the oceans held different secrets. These creatures carry within themselves the memory of geological time, navigation systems refined across millions of years of oceanic wandering, connecting past and future through the continuous present of their floating journey through liquid space. The magnetic highways fade into soft darkness now, becoming part of the gentle rhythm that carries you towards sleep, where dreams may follow their own mysterious navigation systems through landscapes that exist only in the quiet spaces between thoughts. The ocean's invisible infrastructure continues its ancient work beneath your consciousness, guiding countless creatures along pathways that require no maps, no instruments, only the patient wisdom of organisms that have learned to trust the planet's magnetic embrace. Rest now in the knowledge that somewhere in the vast blue darkness, jellyfish are still following their magnetic highways, still reading the Earth's signature with exquisite sensitivity, still maintaining the ancient connections between life and planetary systems that operate continuously beyond the boundaries of human awareness, carrying forward navigation wisdom that predates human civilization and will continue long after our cities have crumbled into oceanic sediment. Let the gentle pulsing of jellyfish bells carry you deeper into peaceful darkness, where magnetic fields become lullabies and ocean currents whisper stories that need no words, only the quiet understanding that comes with surrendering to forces larger than individual consciousness, trusting in navigation systems that operate beyond thought, beyond worry, beyond everything except the simple miracle of creatures that read the planet's heart and follow its guidance home. End of script. Sweet dreams.